Let's take a minute to review the results from the previous two lectures on cosmology. Homogeneity and isotropy tell us that the metric can be written in the Robertson-Walker form. That's ds squared equals minus dt squared plus a of t squared times dr squared divided by 1 minus k r squared plus r squared d omega squared. So that's the Robertson-Walker metric. Where this parameter k is equal to either plus 1, that's for the closed cosmology, where space is a 3-sphere, minus 1, that's the open cosmology, where space is a 3-hyperboloid, or 0, where space is flat. And this function a of t is called the scale factor. Now when we apply the Einstein equations to the Robertson-Walker metric, we obtain an equation for the scale factor, which is a dot squared equals minus k plus 8 pi over 3 times rho times a squared. And this is the Freedman equation. Where rho is the total energy density. And in the standard cosmological model, we assume the energy density is comprised of 3 components: an ordinary matter component, a radiation component, and a dark energy component. So this is, M stands for matter. So this is baryonic matter, atoms and molecules and so forth, and it includes dark matter. R stands for radiation, and D is the dark energy. Now currently in our universe, so our universe now, the matter component comprises about 32% of the total energy density, and of the 32%, it's 28% of it is dark matter. So only about 4% is baryons, atoms, and so forth. Very small percentage is radiation, maybe 1/100th of a percent, and the remainder, 68% roughly, is dark energy. So these are the percentages now, but if we go back in time, the percentages were different. And we can see that by recalling that the matter energy density is proportional to 1 over a cubed. The radiation energy is a constant over a to the 4th, and the dark energy component is just a constant. Of course, we also know the universe is expanding, so a is getting larger with time. Or said another way, if we go back in time, a becomes smaller. So as we go back in time, these components of the total energy become more and more important. In fact, if the universe began in a Big Bang, where a is equal to 0, then in the early moments of the universe, the most important component of the energy, according to this model, would be the radiation component. Now in the field of cosmology, it's common practice to introduce a set of rescaled variables. So we define t tilde to be t divided by the Hubble time t sub h, and we define a rescaled scale factor, a tilde of t tilde, equals a of t divided by the present value of the scale factor, which we call a sub 0. As an aside, let me remind you that the Hubble parameter is defined as a dot over a. So this is a function of time t, and the present value, where we denote the present time by t sub 0, present value of the Hubble parameter we call h sub 0. That's just h evaluated at t sub 0. That's the present value of a dot divided by the present value of a. And the Hubble time, t sub h, is just 1 over the present value of the Hubble parameter. For our universe, observations show that the present value of the Hubble parameter is approximately 72 kilometers per second per megaparsec. And the inverse of h naught, t sub h, is approximately 14 billion years. Now, in terms of these rescaled variables, the Freedman equation can be rewritten as follows. A tilde dot squared equals omega sub k plus omega sub m over a tilde plus omega sub r over a tilde squared plus omega d times a tilde squared. Now these constants omega m, omega r, and omega d are just proportional to the present day values of the energy density of matter, radiation, and dark energy. So omega m in particular is defined as 8 pi times the present value of the matter energy density, so I'll call that rho sub m0, divided by 3 times the present value of the Hubble parameter squared. Omega r is 8 pi rho r0 divided by 3 h0 squared, and omega d is 8 pi rho d0 divided by 3 h0 squared. Now this constant omega k is defined as minus k divided by a0 squared, so a0 is the present value of the scale factor, times h0 squared. And these four constants, the four omegas, are not independent from one another. They satisfy 1 equals the sum. So 1 equals omega k plus omega m plus omega r plus omega d. We can now solve these equations for various choices of the omega parameters to obtain various model universes. And these model universes are usually referred to as Freedman, Robertson, Walker cosmological models. Or FRW cosmologies. Let me describe in a little more detail how we can build one of these FRW cosmologies. The first step, we need to specify numerical values for omega m, omega r, omega d, and the present value of the Hubble parameter h sub 0. And of course, from these values, we can determine omega k. Now the next step is to solve the Freedman equation. So to solve this differential equation, we take the square root of both sides and use separation of variables. In integrating, we have t tilde equals the integral of dA tilde divided by the square root of omega k plus omega m over a tilde plus omega r over a tilde squared plus omega d times a tilde squared. Now this integral determines t tilde as a function of a tilde, so the next step is to invert that relation to obtain a tilde as a function of t tilde. And of course it might not be possible to do this inversion analytically, you might have to do it numerically. Now when you carry out this integral, there's of course a constant of integration, and you're free to choose that however you like, but remember the present day value of A tilde is 1, so we can define as step 4 the present value of T tilde, we'll call that T tilde sub 0, as the value of T tilde when A tilde equals 1. So we just set A tilde equal 1 in this expression to find T tilde sub 0. So this is the value of T tilde now, meaning at the present time. And likewise, most of these cosmologies will have a Big Bang, so we can define the T tilde value of the Big Bang by just setting A tilde equals 0. So this is the value of T tilde at the Big Bang. The next step is to determine whether this model cosmology is open, flat, or closed. So open, flat, or closed. And we do this by examining omega k. So remember, omega k is defined to be minus k divided by A0 squared times H0 squared. So if omega k is positive, that tells us that the parameter little k is minus 1, which means we have an open cosmology. So space is a hyperboloid. And furthermore, we can use the numerical value of omega k to determine the present day value of the scale factor A. So we find A0 equals 1 divided by the square root of omega k times H0. And remember, H0 is one of the quantities we specified at the beginning, so we know its numerical value. Now, if omega k is less than 0, that tells us this k parameter is plus 1, and our cosmology is closed. And again, we can solve for the present day value of the scale factor. A0 equals 1 divided by the square root of absolute value of omega k times H0. And of course, if omega k is equal to 0, that tells us the k parameter is 0 and the universe is flat. Now in this case, we can't solve this equation for the present value of the scale factor for A sub 0. And that's for good reason, because in the flat case, the present value of A doesn't have any intrinsic geometric meaning. So remember, the metric for space-time, the Robertson-Walker metric, looks like minus dt squared plus A of t squared times, in this case, the flat metric, dr squared plus r squared d omega squared. And now just by a simple change of coordinates, we can rescale the scale factor. In other words, we can replace this scale factor with some constant times the old scale factor and absorb that constant into r, into a new coordinate r, which is the old coordinate divided by c. And this leaves the metric unchanged. So the scale factor itself is only defined to within an overall constant. And in particular, the present day value of the scale factor can be anything we like by just adjusting this constant c. So in particular, in this case, the flat case, it's convenient to simply choose the present day value of the scale factor to be 1. And now the final step in constructing our cosmological model is to write down the scale factor, which from the definition of A tilde is equal to A0 times A tilde taken as a function of t divided by th, the Hubble time. So the Hubble time is just 1 over the present value of the Hubble parameter. And we can also find the present day value of the time t in ordinary units like years. It's related to the present value of t tilde by just multiplying by the Hubble time. And also the time of the Big Bang would be the t tilde time times t sub h. Now let's spend a little bit of time discussing some of the implications of these cosmological models, these FRW models. These models assume a matter content for the universe that's a mixture of ordinary baryonic matter plus dark matter, radiation, and dark energy. The density of matter scales like 1 over A cubed. density of radiation, like 1 over a to the fourth, and the dark energy density is a constant independent of the scale factor a. Now we know the scale factor is currently increasing, the universe is expanding, and almost all of these cosmological models tell us that if we go back in time, the scale factor shrinks to 0, so the universe starts with a Big Bang. In particular, the cosmological model that best fits our present observations is one that begins with a Big Bang. So let's go ahead and restrict ourselves to models that begin with the Big Bang. So we'll just assume there's a Big Bang. So sometime in the past, the scale factor shrinks to 0. Now at the present time, the universe is about 1/3 matter, 2/3 dark energy, and a very small percentage radiation. But if we go back in time, as A goes to 0, these components become more important. In fact, in the limit as A goes to 0, the most important contribution will be the radiation. That will become dominant as we go back in time. So as A goes to 0, so that's in the early universe, just after the Big Bang, the radiation dominated. One thing we know about radiation is that the density of radiation is proportional to the 4th power of temperature, and this can be computed from analyzing black body radiation. So combining these two results for the radiation energy density, we see that in the early universe, the temperature scaled like 1 over the scale factor A. So in particular, as A goes to 0, going back in time, the temperature goes to infinity. Let me draw a space-time diagram that shows some of these features. So this is the Big Bang, and this is now. So time is running up in this diagram, and also the scale factor is increasing upwards in this diagram. The temperature of the universe decreases as we go forward in time, so it increases going backwards in time. So this is temperature, and also the energy density in radiation and the energy density in baryonic matter. Prior to about 400,000 years, the universe was so hot and dense that atoms weren't able to form. So this is the time in which matter began to condense into hydrogen and helium. This is referred to as the time of decoupling. It's also referred to as the recombination time. The decoupling time is important because this is the time in which the universe became largely transparent to electromagnetic radiation. Prior to this time, the universe was opaque, so electromagnetic radiation was absorbed by the ionized matter almost as soon as it was released. So when we look out into the universe today and we see the cosmic microwave background radiation, what we're seeing is the photons that were released at the decoupling time. So here's our world line, and the photons we see today came from these events at the time of decoupling. So this radiation constitutes the cosmic microwave background. So CMB is shorthand for cosmic microwave background. And the current temperature of this radiation is in the microwave range. It's about 2.7 Kelvin. But when it was released, the temperature of the radiation was about 3,000 degrees. So the radiation has been redshifted, and this corresponds to a redshift distance of about 3,000 divided by 2.7 is approximately 1,100. So this is the basic picture of the evolution of our universe. This is sometimes referred to as the standard model. where the major events are the Big Bang and recombination. Let me make a few comments about the Big Bang. Big Bang is the time in which the scale factor goes to 0, the density goes to infinity, and the temperature goes to infinity. But the Big Bang didn't occur at some location in space. The Big Bang occurred everywhere in space. So everywhere here is the Big Bang. Sometimes you hear the Big Bang described or pictured as an infinitesimally small, dense ball of matter that explodes outward and expands. Of course, then you have to ask, what is it expanding into? Empty space? Well, this is of course wrong. The Big Bang occurred in all of space. In fact, space is homogeneous, so it must have occurred everywhere. Now the question, how big was the universe at the Big Bang or just after the Big Bang, is a different question. So here's our world line, here's another cluster of galaxies, another cluster of galaxies. And as we go back in time, the scale factor is shrinking to 0, so the distance between these clusters of galaxies is shrinking to 0. But space itself, if it's an open or a flat cosmology, then space is infinite. So even in the limit as we approach the Big Bang, space is still infinitely large. Now if space is a closed cosmology, if space is a three-sphere, then yes, the volume of that three-sphere does go to 0 as you approach A equals 0. Now there are several problems with the standard model, things that we don't understand, and I'd like to discuss two of them in particular. The first is referred to as the flatness problem. Recall that the energy density of ordinary matter, radiation, and dark energy, the present day values are proportional to these omega parameters, and omega m was about 0.32, omega d is about 0.68, and omega r is very small, on the order of 10 to the minus 5 or so. And these parameters must satisfy 1 equals omega k plus omega m plus omega r plus omega d. Now the fact that these three add up so close to 1 means omega k is very close to 0, which tells us that the universe is flat or very close to flat. So these values, which come from the present day observations of the energy density of the universe, imply that the universe is nearly flat, meaning space has a geometry that to a high degree of approximation is a flat geometry. Now to understand why this is a problem, let's take a look at the Freedman equation. That's a dot squared equals minus k plus 8 pi over 3 times the total energy density times a squared. Now let's define the value of the energy density that makes k equal 0. So the value of rho that makes k equals 0, which corresponds to flat space. We'll call that the critical value. Rho sub c. So solving this equation for rho with k equals 0, we find rho sub c equals 3 over 8 pi times a dot squared over a squared. And of course that's just the Hubble parameter. So this is 3 over 8 pi times h squared. Now with this definition we can rewrite the Freedman equation as rho sub c equals minus 3k over 8 pi times a squared plus rho. So all I've done is I've multiplied this equation by 3 over 8 pi and also divided through by a squared. Now this equation can be rearranged to give rho c minus rho times a squared equals minus 3k over 8 pi. Now let me divide this factor by rho and multiply this factor by rho. So what we have is rho c over rho minus 1 times rho times a squared equals this constant. This is a constant in time. Now here's the problem. The product of this factor and this factor remain constant in time. But as we go back in time, this factor, so back in time, this factor goes to infinity. Remember, rho is going to be dominated by radiation in the past, and this is proportional to 1 over a to the fourth. So a squared divided by a to the fourth is going to blow up as a shrinks to 0. So this factor goes to infinity. It's multiplied by this factor, which must then go to 0 as we go back in time. So as we go back in time, the energy density in the universe had to become closer and closer to the critical density, the value of the density that makes the universe flat. So the fact that the present day density is close to the critical density means that in the past it must have been infinitesimally close to the critical density. So the initial conditions for the universe, the conditions that came out of the Big Bang, must have been very finely tuned or finely balanced to give us the nearly flat universe that we see today. So another way of expressing the flatness problem is to ask the question, how could the initial conditions be so finely balanced to give us a present-day universe that's nearly flat? Now the next problem I want to discuss with the standard model is called the horizon problem. The horizon problem is a generic problem for all of these Big Bang cosmologies, but I think it will be interesting to describe it in concrete terms using the present-day observational data for our universe. So as an example, let's take our universe, which you'll recall has omega m equal about 1/3, omega radiation is close to 0, omega dark energy is about 2/3, and omega k is approximately 0. By the way, this particular model is often referred to as the lambda CDM model. The lambda in the name comes from the dark energy. Remember, dark energy contributes to the Einstein equations just like a cosmological constant, and the symbol for a cosmological constant is lambda. So this refers to the dark energy, and the CDM refers to cold dark matter. So remember, most of the matter content is dark matter, with a small fraction of that being baryonic matter. And remember, this component of the universe is cold in the sense that we modeled it as a pressureless dust. So the name lambda CDM comes from the fact that we're modeling the energy density of the universe as primarily dark energy and cold dark matter. And sometimes people will include a small amount of radiation in these models. But for simplicity, let's just take these as the parameters of our cosmological model. And to complete the specification of the model, let's take the Hubble time, which is 1 over the present value of the Hubble parameter, to be 14 billion years. That's 14 times 10 to the 9th years. Now for this model, we can compute the scale factor analytically. Just following the steps outlined earlier in this lecture, we find A of t is equal to 1 over square root of 2 times hyperbolic sine of square root of 3/2 times t over th. All of this to the power 3/2. We also find for this solution that the time of the Big Bang is 0. That's the time that A is equal to 0. The current time, the now time, is square root of 2/3 times arc sinh of square root of 2 times TH. And that's approximately 0.936 times TH. And the current value of the scale factor is 1. Now recall the time of decoupling is about 400,000 years. This is the time atoms formed and the photons were released that we currently see as the cosmic microwave background radiation. So this is about 2.9 times 10 to the minus 5 Hubble times. And the scale factor at the time of decoupling was about 8.5 times 10 to the minus 4. So it was quite small compared to the current value of 1. Let me draw another space-time diagram. So here is the time of the Big Bang, here's decoupling, and here's now. So this is Big Bang time, which is of course 0. This is the time of decoupling, and this is now. This is our world line. And here are the photons that we see released at the time of decoupling. Now in this two-dimensional diagram, these horizontal lines are radial lines. So let's place ourselves at the origin, so at coordinate value little r equals 0. And this event will take to be coordinate value capital R, little r equals capital R. What I'd like to do now is compute the proper distance between this event and this event. So as we look out into the sky, we see the cosmic microwave background in one direction coming from this event, and if we look in the opposite direction, we see the photons coming from this event. So let's call that distance d. So this is the distance, the proper distance between the cosmic microwave background radiation photons that we see when we look in opposite directions in the sky. And I'm going to put a little subscript p on here because it's the distance as determined by the past light cone, our past light cone at the time of decoupling. Now the distance between us at the time of decoupling, this event, and this event is just half of the distance that we want. So this is d sub p divided by 2. So how do we compute this distance? Well, let's recall that the Robertson-Walker metric along a t equal constant slice, along a constant radial direction, is just a of t squared times dr squared. More generally, it's dr squared divided by 1 minus kr squared, but remember we're assuming the universe is flat, so k is equal to 0. So that means we can ignore this factor. So now taking the square root of both sides and integrating, what we find is the proper distance dp over 2 is equal to a at the time of decoupling times the integral of dr, which is just capital R. And now we find capital R by integrating the Robertson-Walker metric along this null ray. So along a null direction, ds squared is 0. So that's 0 equals minus dt squared plus a of t squared times dr squared. And again, we drop the factor 1 minus kr squared since k is equal to 0. And also d theta and d phi are 0 since this null ray is along a radial direction. Now let's separate variables. What we find is dt divided by a of t equals dr. And of course we can integrate. So we integrate from 0 to capital R, and the t integral goes from the decoupling time to the present time t0. The right-hand side here is of course capital R. So what we get by combining these two results is d sub p equals 2 times a at the time of decoupling times the integral from t decoupling to t0 of dt divided by a of t. Now let's file this result away for a moment and consider a similar calculation where we start with the Big Bang, and this is the decoupling time. And let's consider the future null cone of an event at the Big Bang. So we can think of this as the path of light rays that are released at the Big Bang and reach the decoupling surface. Of course, light can't really travel freely during this period in the history of the universe, but the future null cone still represents the region of causal influence for this event. So let's compute this distance from this event to this event. Let's call it d sub f. The subscript f refers to the future null cone here. This is the distance of causal influence of an event at the Big Bang. So let's let this have coordinate value r equals 0. This is coordinate value capital R. Now by integrating ds equals a of t dr, we find that df over 2, that's the proper distance from this event to this event, equals a at the decoupling time times capital R. And now integrating along this null direction, the null direction satisfies minus dt squared plus a of t squared dr squared equals 0. We find the integral of dt over a of t equals the integral dr, and that's from 0 to capital R, which of course gives capital R. And the t integration ranges from the Big Bang time, which is 0, to the decoupling time. So that's from 0 to t decoupling. And now combining these results, we find df equals 2 times the scale factor at the decoupling time times the integral from 0 to t decoupling of dt over a of t. Now let's compute this result along with our result for the distance d sub p using this expression for the scale factor. Right? Well, when we do that, we find that the distance d sub p, this is for the lambda CDM model, d sub p is about 70 million light years. D sub f is about 2 million light years. So the point being d sub p is much, much greater than d sub f. Let's take a look at what this is telling us. So here's the Big Bang. Here's the time of decoupling, and here's now. So this is T0, T decoupling, and T Big Bang. Here's our world line. Here's the light that we see from the decoupling time that's released at the time of decoupling. And this distance from this event to this event is about 70 million light years. On the other hand, if we look at the future light cones of events coming from the Big Bang, they span a distance of only about 2 light years. So, for example, this would be one light cone. Here's another light cone, another light cone, and so forth. And similarly over here. So you can see that since these light cones only span about 2 million light years at the time of decoupling, the set of events in the very early universe that could have causally influenced these events were widely separated. So for example, for this event, the set of events that could causally influence this event are here. The set of events that could causally influence this event are these. The point is that these two events, let's call them E1 and E2, were never in causal contact with one another. So this is the horizon problem. The problem is to explain why the cosmic microwave background looks the same in all directions. So it's not only the same temperature, but also the small fluctuations in temperature have the same spectrum. So how can that be when these regions of the universe were never in causal contact? So there was never an opportunity for those parts of the universe to come to any kind of thermal equilibrium. And as I said before, this horizon problem is a generic problem of all of these cosmological models, not just of the lambda CDM model. So how do we solve these problems with the standard cosmology, in particular the flatness problem and the horizon problem? Currently, the most popular explanation is that the universe underwent a period of rapid inflation just after the Big Bang. Let's see how this works. Here's a graph of the scale factor as a function of time for our simple lambda CDM model. So this is scale factor on the vertical axis, and the curve for the lambda CDM model looks something like this. So this is lambda CDM. And we are currently about right here on the curve. So this is T0, and the scale factor right now is 1 in this model. And we're just beginning to enter this period of exponential growth driven by the dark energy. Now the origin of the graph, where A equals 0, is of course the time of the Big Bang. And by the way, you can easily check that for this model, for small t, the scale factor varies like t to the 2/3 power. Now on a linear time scale, the time of decoupling would be really close to the Big Bang, but I'm going to stretch this out in this picture and put the decoupling time here, just so that I can show what's going on in the very early universe more clearly. So this is not a linear time scale. So the idea behind inflation is that the universe underwent a brief period of very rapid expansion shortly after the Big Bang. So let's say the brief period is here. Then this curve is modified to look something like this. So now it begins this period of inflation, and it grows very rapidly, and then continues with the current model we see today. So this would be the lambda CDM model with inflation. So this is the brief period of inflation. Which was thought to take place around 10 to the minus 35 seconds after the Big Bang. And during this time, the scale factor increases by 30 orders of magnitude or more. So what could cause the universe to expand like this? Well, one possibility is that the energy density goes through a period where it's dominated by a constant component. So inflation could be caused by period with constant energy density, constant meaning independent of the scale factor. An example of constant energy density is dark energy. So this is like dark energy, otherwise known as the cosmological constant. But in this case, in the inflationary period, it might be distinct. So it might be distinct from the dark energy that we have today. So if we have a period in the early universe where rho is equal to a constant, then the Freedman equation tells us, remember, a dot squared equals minus k plus 8 pi over 3 times rho times a squared, and we'll take k to be 0, then a dot squared is proportional to a squared, since rho is a constant, which tells us that, of course, a dot is proportional to a, so a is an exponential. So during this period of inflation with a constant energy density, the scale factor grows exponentially. Now, how does this solve the flatness problem? Recall that we can write the Freedman equation as the critical density over the density minus 1 times the density times a squared equals a constant, where this critical density is the value that the density needs to be for the universe to be flat. Now, without inflation, and going back in time, we have rho a squared goes to infinity. That's because rho is dominated by the radiation component, which goes like 1 over a to the 4th power. So since this factor goes to infinity, this factor must go to 0. So in other words, rho becomes closer and closer to rho c, the critical value, as you go back in time. But we know that rho is approximately rho c now, so it must have been much, much closer to rho c, the critical value, in the past. And the problem is to explain this fine-tuning of the energy density. But with inflation, we have a period where, going back in time, rho a squared goes to 0, and this allows rho to diverge from the critical density going back in time. Said the other way around, the initial value of rho near the Big Bang does not need to be close to the critical density rho c. So it does not need to be close to rho c. As the universe goes through the inflation period, rho a squared increases by many orders of magnitude, which means this factor decreases by many orders of magnitude. So inflation drives rho to the critical value, rho c. And the universe we see today is very nearly flat. How does inflation solve the horizon problem? Well, if you'll recall, the size of our past event horizon at the time of decoupling was given by this proper distance I call d sub p. That's 2 times a at the time of decoupling times the integral from the decoupling time to the present time of dt over a of t. And the size of the future light cone for events near the Big Bang is 2 times a at the time of decoupling times the integral from the time of the Big Bang to the decoupling time of dt over a of t. Now, without inflation, we have the problem that dp is much, much greater than df. What about with inflation? Well, you'll notice these quantities dp and df depend on the scale factor at the time of decoupling and integrals over the inverse of the scale factor over different ranges, from decoupling time to the present time for dp and from Big Bang to decoupling time for df. But the curve, with and without inflation, you'll see it's only modified for times between the Big Bang and the end of inflation. So in particular, the scale factor at the time of decoupling isn't changed by inflation. And in fact, this entire integral over the inverse of the scale factor from the decoupling time to the present time is the same. So said another way, the size of our past event horizon isn't changed by inflation. So that means dp is the same with and without inflation, but df is larger. And this is because during the time between the Big Bang and inflation, the scale factor is 30 orders of magnitude or more smaller. So that makes this integral much larger, even if the time between the Big Bang and inflation is small. If this scale factor is small enough, we can make the integral as large as we like. So df can be as large as we like by adjusting these parameters in a suitable way. And we can avoid this horizon problem of dp being much larger than df. Let me sketch a spacetime diagram showing these future and past light cones with inflation. So here's the time of the Big Bang. Here's the decoupling time. Here's our current time. So this is T naught, T decoupling, T Big Bang. Here's our world line. Here's the cosmic microwave background radiation that we see released from the time of decoupling. So these are the events I call E1 and E2. And the distance between E1 and E2 is what I call d sub p. Now, the future light cones from events at the Big Bang, with inflation, they're very much larger than they were without inflation. So here would be a future light cone. Here's another future light cone. And these have width d sub f. And so forth. I can draw a few more in here. So you can see in this case there's plenty of overlap here at the time of the Big Bang, sets of events that can influence both E1 and E2. So these are events in the causal past. Of both E1 and E2. So there's plenty of time for information to be exchanged back and forth between the regions of the universe that evolved to E1 and E2. So with inflation, the cosmic microwave background radiation that we see today comes from regions of the universe that were able to come into thermal equilibrium in the past. There's one question we still need to address. How do we arrange for a period of inflation, for a period in which rho is approximately constant in the early universe? Most schemes for inflation rely on the use of a scalar field called the Inflaton Field. So it's a scalar field, phi. The action for the Inflaton field is integral d4x square root of minus g, that's the volume element in curved space-time, minus 1/2 g mu nu del mu phi del nu phi minus v sub t of phi. This function v of t is the potential, and it depends on temperature. T. So now the equations of motion that come from this action are del mu phi equals partial v sub t with respect to phi. And the stress energy momentum tensor for this Inflaton field is del mu phi, del nu phi, minus 1/2 g mu nu, del sigma phi, minus g mu nu times v sub t of phi. In one of the early proposals for inflation, sometimes called the new inflation, the potential looks like the following. So here's the phi axis, here's the potential v sub t of phi, this is the phi axis. Well, for high temperatures, the potential curve looks something like a parabola. So this is high temperature. And for low temperature, the curve looks something like this. So this is low temperature. And for intermediate temperatures, it looks something in between. So before inflation began, the temperature was high, and the potential curve looked like this. And a solution for phi to the equations of motion is just phi sitting at 0, sitting at the bottom of this potential. So phi equals 0. Phi equals a constant means the left-hand side here is 0, and phi sitting at the bottom of this potential well means dv d phi equals 0. So this is a solution, and you can see that the stress energy momentum tensor for phi equals 0, this term is 0, this term is 0, we simply have T mu nu equals minus G mu nu times V sub T at phi equals 0. So this is just like the stress energy momentum tensor for dark energy or cosmological constant. With energy density equal to minus V sub T at phi equals 0, which is a constant. So this is the solution before inflation, or perhaps we should say at the beginning of inflation. But after inflation, the temperature drops, so the potential energy curve looks like this, and the solution then shifts to here. Let's call this value of phi, I don't know, let's call this phi hat. So this is the solution after inflation. We have low temperature, phi is equal to the constant value phi hat, and the stress energy momentum tensor is minus G mu nu times V sub T evaluated at phi hat. So in this case, the energy density is minus V sub T at phi hat, which could be very much smaller than the energy density before inflation. And it could be that this contribution to the energy density today is insignificant, or it could be that this is the dark energy that we see today. This particular scheme for inflation that I just described, sometimes called the new inflation, has some problems of its own. So although inflation solves some of the problems with standard cosmology, we don't yet have a real understanding of how inflation would come about. There are lots of other schemes for inflation that have been proposed, but none of them are truly satisfactory. Nevertheless, the idea of inflation is pretty compelling, and it appears to solve the flatness problem, the horizon problem, and as well as other problems. So as a result, inflation has been around for a long time, for about 30 years, and it probably isn't going away anytime soon.